Hi guys! Working a model under Linux operating system can be quite different than working in a bare metal environment. For this tutorial I chose the Simple DMA module, which need a memory space for the TX and RX buffers and the memory space for the registers. And it's a very simple module, so I can show you how to work the Linux with a model, even if you write it and you have register in it. Now the main difference in working under Linux is that Linux uses virtual addresses. The Linux remap the memory space and provide the user a virtual address and not the physical ones. The DMA need the physical address because the DMA doesn't know that it's under Linux operating system or in a standalone in a bare metal environment. So to overcome this problem, we can define a physical memory space in the memory of the FPGA, address virtual address to it using the mmap command, and then we will have a memory space defined as a virtual addresses, but we know the physical address. Then we can transfer the physical address to the DMA to make it work. Now I want to remind you how we work the DMA. The DMA needs two parameters to make a transaction. It needs address to read or write from, and it needs size, how many bytes. The Simple DMA has 4 registers, 4 for TX and 4 for RX. It has the control register, the status register, the address either for TX or RX, and the length for either the TX and RX. Writing to the length register starts the DMA. In my Simple DMA example tutorial, I use functions in the dma.h file. Here I will be working straight with the registers. So the first thing we need to do is generate a reset using the control register, both TX and RX. Then we need to give the address for both TX and RX. Then we need to enable both TX and RX with their control registers, and we'll give the length like we did in the Simple DMA example. First the RX and then the TX. The TX will start working, and then we can make polling on the status register to see whenever the DMA finished its work. This is done for both TX and RX, and this will be the transaction. And after we finish the transaction, we need to close the memory spaces that we use, both for the memory spaces and for the register memory space. I'll start by going to my GitHub. Here in my GitHub, I have a repository DMA, and in here I have a branch Linux DMA. I'll clone this into my demo folder. And I'll switch to Linux DMA branch. Now here it is. And here I have a simple DMA tickle script. I'll open my Vivado. I'll cd to my demo folder, DMA work, and I'll source the Simple DMA tickle script. This is all explained in my how to save a Vivado project in source control. Here it is. Now I have exactly the same project as I had in my basic DMA example tutorial. Here is a DMA without the scatter gather, simple DMA with read and write. We also have here an ILA with 4096 samples, and we can compile. This is all done in my simple DMA example video in the tutorial, so I won't repeat it here. So I'll just generate a bitstream. I'll stop my video and come back when it's done. My bitstream is done, so let's view the reports. I have no timing issues, so we can move to the software. Before we build the Linux, I want to see that my design is working. So I'll export the hardware with the bitstream to my FPGA software. And here it is. Now I'll open Vitis. We'll direct it to my FPGA software directory. And we'll open an application project. First we'll do a bare metal test to see if the design is working and how it's working. Next we'll bring our XSA. We'll call this Simple DMA bare metal project, core 0, standalone, and an empty application. Now we'll create a file, new file. We'll call it Simple DMA bare metal.c, and we'll start writing the bare metal application. I'm copying this for my GitHub, so you'll have the source code there. First we'll bring the include. This time we won't be using the AXI-DMA.h I will go straight to the registers because it's easier here and it's simpler using the Linux for the beginning. Next we'll define the memory space. We're checking that we're on the zinc, and we start with the DDR base address plus 10 million. We'll need a TX buffer and an RX buffer, which will be above our memory space with 1000 and 2000. I need some parameters. The packet length and the start data count, and we'll need the pointer for the DDR. This is part of the X parameters file, which indicates for the address the block design gave to my DMA. This is all explained in my Simple DMA project. Now we'll give the main and end the main. Now the DMA will use straight the registers, so we'll need the project guide of the DMA, the PG021 DMA, and here are the registers. Here, for the Simple DMA, which is this, we have 4 registers to TX and 4 for RX. We have a control register, which we actually need 2 bits here. The reset, so this will reset the DMA, and the enable. This will enable the DMA to start working when the length is written. The next is the status register. This checks if the register is working. Here we need the idle bit. Here the idle bit. If it's 0, it's not idle. That means the DMA is working. If it's idle, it means it's ready to work. We will wait until it will be 1. The 2 more registers for the TX is the source address, which will configure, and the length. Writing to the length register, which actually started DMA, either in TX or in RX. So all the configuration above is, you just write them, and then once you write to this register, the DMA start. We will start first the RX to be ready for the TX to start working, and once the TX start working, the DMA will start work, and we'll wait for the idle bit. So for this, first we need to have data. We will generate data in an array at the TX buffer base, which is the 1000 bytes in hexa above the memory space address. Then we will add a value with the start data count, and we will increase it by 1 at each cycle. And after this is done, we will write it, we will flash the cache to have it in the DDR itself and not in the cache. Now let's start working on the DMA itself. For the DMA itself, like I said before, first we reset the TX and we'll read it, then we reset the RX and we'll read the control register. Then we give the address for the TX and the RX from here. Then we will check the control register and add 1 to enable the TX. Once it enable, a write to the length will start the DMA, both the TX and the RX. Then we'll write the length to the Rx, which will start the Rx, but the data isn't coming yet. And then we'll write the length to the TX, and then the TX will start send, the FIFO will transfer, and the Rx will start receiving. Now we wait for the idle to be 1. So we check the BZ, and with the second bit, if it's 0, it's still running. Again, the same for the Rx. So as long as either of them is running, we will keep reading and checking. Once it's done, both of them are idle, the transaction is finished, and we can invalidate the cache. So we invalidate the TX buffer, which actually didn't change because we just read from it for the packet length size, and we will invalidate the Rx buffer, which the DMA transferred data to. So this is actually the software for the bare metal. I'll save it, compile it, and before I move to the board, I want to add my camera. And I remind you this jumper. This jumper has to be on the JTAG position when we're working with bare metal. Later on we will move to Linux and we will move it to this SDK position, but now it's in the bare metal position. That was the idea of the camera, so we don't need it anymore. And we can connect our board. Now the software is compiled, so we can move to debug configuration, single application debug. We will reset the entire system, program the FPGA, and debug. Now before we start debugging, we want to see the memory spaces. So I'll add my memory viewer with the address for the TX and the Rx. And to see the DMA working, I'll open my hardware manager. I'll connect to the board. And since this is the project that actually built this design, it's familiar with it LTX, which is the ILA file, so it opened it. We will go, here is the FIFO, here is the TX output, these are the connection to the DDR, and this is my interface to the zinc. So we want to see the reads and the writes. So I'll add the address read value, and I'll add the address write value, and I'll OR them. So either one is turned on, I will trigger the ILA, and we'll start at 100 samples, and my ILA is ready, and my software is ready, so we can start debugging. First we'll write the data. So I'll stop at the beginning of the DMA. Here is the TX buffer. we write the data. Here it is. And we flashed it to the cache. So it's ready. Now let's start the DMA. And our ILA caught it. So here are the transactions. Here is what we wrote. We reset the TX, we reset the RX, we give the address for the TX, we give the address for the RX, we enable TX and RX, and we start the RX, we start the TX, the data is coming out from the TX and received by the RX, and we see here our loop that in the beginning the TX and the RX are working, then the TX finished work, we have the two, but the RX didn't, then we have both RX and TX back to idle, so the transaction is finished. And now we can check the data. We'll refresh, we'll invalid the cache for the TX. Nothing happened because the TX didn't change by the DMA. It was just read. And the RX received the data from the TX. So we know our design is working and everything is cool. So we can move to the Linux. For the Linux, first we need to copy our XSA to my Linux shared folder. And now I'll open my Ubuntu machine. I'll start a new terminal. First of all, I'll source the Petalinux setting.sh file. And now we have Petalinux in our system. This is all explained in my Linux tutorial. I will just go very fast on it now. So I have here Xilinx directory, which I want to build my Simple DMA project in. So first I'll bring from my shared folder, I'll bring the XSA. So this requires root permission, so I'll sudo ls shared. I'll add my password. And here is my XSA. So I'll sudo cp shared folder XSA into here. Here it is, but it's still under root permission. So I still need sudo to change owner. So ch own ud. Now it's under UDI permissions, so I don't need the sudo anymore. I'll change mode to 777. And my XSA is ready. So now we will create a Petalinux project. So it's Petalinux create. Minus type project minus template zinc, because we're working in the zinc 7000 series, and minus minus name, and we'll call it Simple DMA Linux. And here it is. We'll cp the DMA into it, and we'll cd to it. And here it is. Now we need to configure our Linux project. Petalinux config minus get hardware disk shan. This will open a console. Again, this is all explained in my Linux tutorial. I will have the link below. And we will go with the default, so we'll save and exit. So my project is configured. What left is to build. This will take a while, so I'll stop my video and come back when it's done. Okay, so my build is done, so it's now time to move to packaging. Here is the image. Again, this is all explained in my Linux tutorial. This is the image. Under the image we have Linux. Here we have all the files created by the build, and now we need to do package. Peta package minus boot minus fsbl, and the fsbl of the zinc. We're working with zinc. Minus FPGA and the bitstream. Minus u minus boot. And we have the boot.bin, the boot.scr, and the image, which is the kernel. So now we can copy this to our shared folder. We'll need sudo again, sudo ls shared, and my password, and we sudo cp to my shared folder, the boot.bin, the boot.scr, and the image. And here they all are in the Linux, and here they are in the shared folder. So we finished with the Linux. We can close it. Now I'll put my SD card in my computer. I'll format it. And I'll copy the 3 files into it. And we're ready to move for the board. I'll eject the SD card, and now I'll open my camera again to show you the thing they do on the board. First, we have the CD, and we need to put it in the socket here as we did in my Linux tutorial. Now again, the jumper for the Linux, the jumper should be at the SD position. Now my board is connected to my router, so it will get an IP, and we need this IP, and that's it. I'll open my term. And I'll connect my board. Serial port 515200, and here the Linux is booting up, and as you see, my ILA recognized the board and it's already connected. And I will disconnect the bare metal software because we need a new bare metal. Now for the Linux application, we again need the XSA, so I'll go to my demo board directory. I'll take the XSA from my FPGA with the bare metal and move it to software, and we'll open a new Vitis. We'll direct it this time for the software directory, and here it is, and we'll create an application project. Again, we need the XSA, I can close my camera, we're done with it for now. We'll call it Simple DMA, this time Linux, and we need the SMP for both cores. And we have the Linux operating system and Linux empty application. Now we go to source, and we'll add a new file. We'll call it Simple DMA, this time Linux.c, and again I'm copying this from my GitHub, so you'll have the files later. First we need the includes. These are the includes for the Linux. Now the main issue in the Linux compared to the bare metal is that here in the bare metal we just needed to state the address and point a pointer to it. In Linux it's a little more tricky because the Linux uses virtual addresses and not the physical addresses, so we need to make some changes to have the known address and use it. So first we define the memory space for the data. Again, 10 million, and we define 10,000 bytes for the size, for the TX and the RX, and the TX and the RX definitions. And here it is. Now we'll bring the main, we'll start the main. And we'll end the main. Okay, first we need to have this memory location for the Linux to address and to use. For this we need to open a file. In the Linux system we have the dev.mem file. Here is the Linux system, and we can see we have a file here that describes all the memory locations. So we open this file from the Linux system. We need a variable for it, an integer for it, and we need a variable to use it. So the command to address this memory space is the mmap command. Now it's a little tricky because I'm telling you the Linux here, I want this address, I want it. I determined that this is it. Usually the Linux finds the right location in memory and decide for itself, but here I make sure that this is the memory so I can have the addresses to the DMA. The Linux might use this address space for something else, and then you will have a crash. So it's important to make sure that this memory space is available. Now you can see in the Linux system we have a proc iomem file. Here it registers where the Linux has. It has the memory, the system RAM at 1 to 10,000, 10 million and FFFFF. The kernel itself use 8,000 to B1000. The kernel data is used C to C6 whatever. So these are definitely places that we can't use. Here we have some other issues like the internet controller, the TPIO, a lot of other things that we can use. So again, these are not available space. So 10 million looks like a good choice. So this is what we did. So now we have a memory space that defined for 10,000 bytes, and we can use it. So first let's define two arrays, one for the TX and one for the RX. Now you define the pointer, give it the address of the DDR mem. This will be a virtual address with the relative address, and then define the pointer for the buffer, for the TX buffer and for the RX buffer. Next, we want to check that we can address those addresses. So I add here, because we don't have in the Linux, the memory viewer is not available like it was available in bare metal. Here we could use the memory viewer, but in Linux we can't. So not in virtual and not in physical. So we have to actually write the code to see what's in the data. So I write the code. We will need packet length of 20. Here the packet length. So I want to see, now I define this as 32 bits, so I divide it by 4, and I read all whatever in the buffer, the TX buffer, before I write it. And again, for the TX buffer, I'm expecting garbage because nothing happened yet. Next, we need to fill the buffer like we did in the bare metal application. So again, we defined a pointer of this time 8-bit for a byte for the buffer size, like the TX here. And then we started the start command and we filled the buffer for the packet. Now we use a different packet because here we're using in byte and later we will use in 32 bits address. So to write bytes, I'm using byte array. And we see that we wrote what we expect to wrote. Again, it's the same checker that we had before, but now after we wrote it, so we can see the data that is going to be transmitted. This is how you read and write from a memory location in Linux using mmap. Again, it's a little risky. You need to make sure that the address you chose is available, but it's working. It's the easiest way. Next, we need the DMA. Now the DMA, first we need to address registers in the DMA like actually we did here. Here we just add a pointer with the address and we defined an array and we wrote straight to it. Now we'll do the same, but in Linux we need to define a new memory space with an mmap. This time we have to use the mmap because this is a specific address. We know that our DDR here is at 404 address, so we need the address, and since we know we have about 58 addresses here, only 8 register, 100 byte size will be enough, and we will use the mmap this time with the DMA variable that was defined. The memDMA was defined here and used here, and then we will have the DMA mem, which is defined here with the mmap for the DMA base address and the DMA size, like we did for the data, but this time we read and write for specific registers. Now, the function for using the DMA didn't change, just need a new way of writing. Again, we define, if we can look at the old bare metal, you can see it's very similar. We define data and busy 32 bits uint. We define the regs, the reset. We give the address of the TX. Now we need the physical address. The DMA doesn't know if it works under Linux or work under bare metal. So we actually need to write here the physical address. And this is why mmap is a little problematic, because if we have a virtual address, then we don't know the physical address. We don't know what to write here. So we need here the physical address. This time, this is why I created the mmap from the physical address, so I know the physical address. So this is the physical address for the TX. This is the physical address for the RX, like in the bare metal. Here, nothing changed. Again, we'll read the control and add 1 to enable. we give the packet length for the RX, which is make it ready, and we give the packet length for the TX, start the DMA, check the status register for the enable bit, and once they are both finished, we finish the transaction. Again, here we had in the bare metal, we needed to invalidate the cache and actually to flash the cache. In Linux, it do it for us. We opened a memory space and now we finished working with it, so we need to close it. And now we want to check the data. We have the same function that we have here, but this time after the DMA has worked. So the TX will stay the same, the RX will be added, the new values. And since in the beginning, we opened the DDR mem, so now we need to close it. Only now we finished working with the memory space allocated in the first mmap, so we need to close it. And actually that's it. We save this file, we build this file, and we're ready to go to the board. Now, my ILA, like I told you before, it always recognizes my bits, my design. Now, we need to, for the Linux, we need to disconnect the bare metal, make sure it disconnect, and we need to check. Now here we use debug mode by copying this to the Linux board and going back and forth with the Linux itself. So the Vitis must find the board. Now the board, like I told you before, is connected to my router, so it got an IP. So I'll write ifconfig, and here is my IP. But working with Linux, I found out that it's better to give a static IP, so I give ifconfig if168.1.100. I'll check it, and now we have a known IP, so I can write it to the Linux, to the Vitis. Now we can go to debug. Single application debug. Now we need to connect this to the board. This time we need Linux agent. So we give it a name, Simple DMA, and the host. This is why we used a known IP address. We have 192.168.1 and 100. 192.168.1.100. We test the connection and we successfully connect to our board. Now again, after compiling, this file is compiled, it will be copied to this address in the Linux system, and then we can debug it. So let's debug. We don't need the metal anymore, and we need the ILA. So let's use the ILA. While debugging, we have this console, so nothing will actually be written here on the Linux console. We'll start by start. We got the start. Now we defined the memory for the DMA. We open the file. the file was found, no error, and we address it to the DDR memory space. So this is the DDR memory space. We can't see it here, but this is the virtual address. What was 10 million is now B6E21 whatever. Okay, so now we can define the two buffers, the TX and the RX. Again, you see it's the same number but plus 1000 plus 2000, and again here, so it's the same address. We cannot see it, so we'll need to read it. So this is the TX buffer. As you see, it's junk, and the RX buffer, again junk. Now we can write the data to the TX buffer, and once we read the TX buffer, we will have the CDEF like we used in the bare metal. So now we need to define the memory space for the DMA. So again, we reopened the file. We didn't close the old one, but we still open the file here, and we assign a virtual address for the DMA mem here. Now we're ready to start the DMA. Our ILA is ready, and we'll run till the checker. And the ILA found it, and again the same structure as we had before. Reset TX-RX, address TX-RX, enable TX-address, RX length, RX start the transaction, transmit, receive, and the loop, exactly like we saw in the bare metal. From the DMA point of view, there is no different from bare metal to Linux. Then it just gets registers and work it. But now we can check the data in the DMA, in the buffers. Now the TX buffer didn't change, so we still have the CEF. But if I remind you, the RX buffer was junk the last time we check, and this time we check, we'll have the same data, CDEF up to 2B in the TX and CDEF up to 2B in the RX. So this is how we work with Linux and with mmap. This problem, again, if I use the mmap on an area that the Linux needs, it might be a problem. So maybe on my next video I'll show you how to overcome this problem. But this is the easy way to work the DMA, or to work any model that you wrote and had registers and need data in the DDR, and this is the basic option. That's it for now. Hope you find this tutorial useful. Hope you enjoyed it. Thank you and goodbye.